Welcome, everyone. So I'd like to welcome you to the Nauenberg History of Science lecture with Peter Galison, who is the Joseph Pellegrino University Professor in History of Science and Physics at Harvard University. I'm Eli Silver, and I'm the president of the Emeriti Association. This lecture is presented by the UC Santa Cruz Emeriti Association, and is co-sponsored by Crown College, the Santa Cruz Institute for Particle Physics, the Arts Research Institute, and the History Department. So I'd like to say a couple words about Michael Nauenberg. Michael was born in 1934 to a Jewish family in Berlin, and they barely escaped persecution from the Nazis in 1939. They went to Colombia. Michael then, being moved to the US, he received his doctorate from Cornell in 1960, working under Hans Bethe with a thesis on particle physics. He then became a visiting fellow at the Institute of Advanced Study in Princeton, and for the next 5 or 6 years, he was on the faculty at Columbia University and then at Stanford University. In 1966, he came to UC Santa Cruz as a professor of physics, and he was part of the group that started the physics department at UCSC. He was also instrumental in developing both Stevenson and Crown colleges. Since the 1990s, about the time he retired, he published numerous works on the history of science, especially physicists from the 17th century, such as Isaac Newton, Robert Hooke, and Christian Huygens. When Michael passed away in 2019, the UCSC Emeriti Association and the Nauenberg family established this History of Science lecture series in his honor. Tonight, it's the second of this series. So the title of tonight's lecture is Time, Physics, Film, History. And after the talk, there'll be time for questions. The lecture is also on Zoom and will be recorded after the event and made available on the Emeriti Association YouTube channel. So now I'd like to introduce Joel Premack, who's a distinguished professor emeritus of physics at UC Santa Cruz, and he will introduce Peter.
So I'll say a few more words about Michael Nauenberg, since as a physicist I knew him rather well. I first encountered Michael when I was a graduate student at Stanford from 1966 to 1970. Michael Nauenberg was incredibly enthusiastic about anything he worked on. This was true of physics, and later on it was true of history. And he made significant contributions to both of them. One of the remarkable things that Michael's physics work entailed was the proof that if you do a quantum electrodynamics calculation, Feynman diagrams and all that stuff, you find that almost all of these calculations are infinite, they're divergent. But if you add together each of the different possible physical processes and you actually calculate something that's observable, Michael proved, along with the Nobel Prize laureate Tsung-Dao Lee, T.D. Lee, and independently it was shown by the Japanese physicist Kinoshita, that the result is finite. This turns out to have very important consequences, this kind of argument, and it also turns out to be relevant to general relativity, although that's not something that Michael did. But anyway, Michael, after many decades working in particle physics, fundamental quantum field theory, the last couple of decades of his life, he spent really working on history, and as Eli said, he made significant contributions. And I remember encountering Michael after he'd discovered how to interpret some very obscure page in the Newton notes that are still at Cambridge University. He was so happy that he was able to figure it out. And I think other people in the Newton field also appreciated what Michael was doing. I understand that Michael had some correspondence and maybe conversations with Peter Galison about other aspects of the history of science. The first of the Nauenberg lectures was called Isaac Newton and the Origin of Civilization, a subject that, of course, Michael would have been extremely happy to be able to hear, even though he couldn't, because this was given after he died in May of 2022 by Jed Buchwald, a distinguished professor of history of science, especially physics, at Caltech. Well, we're incredibly fortunate to have a really remarkable person giving the second of the Nauenberg History of Science lectures, Peter Galison. Peter is an historian and a physicist, and of course he's a professor of both, and he actually has PhDs in both, effectively. But he's also a filmmaker. And as far as I know, that's a unique combination. I particularly love his book, Empires of Time, Poincaré's Maps and Einstein's Clocks, which I think he's going to talk about. What's extraordinary about that book is that he shows how the practical concerns of measuring the size of the Earth and the distance between spots on the Earth and getting the trains to run on time and not bang into each other if they're going in opposite directions on the same track, which of course required very accurate synchronization of clocks. And Poincaré and Einstein both realized that the synchronization of clocks was essential to understand the nature of time, although Einstein understood it at a somewhat deeper level, as Peter's book explains. Peter's movie, Black Holes, The Edge of All We Know, which I think he's going to also show some short excerpts from, doesn't aim to popularize science the way practically all the science documentaries do, either taking some aspect of science and explaining it in simpler terms, or taking some historical development and popularizing the role of the individual scientist. Instead, what Peter's movie does is to show how science is done. And the way he did it, as I think he'll explain, is to take lots and lots of video in the process of two different things happening. The Event Horizon Telescope to actually see for the first time the tiny little region of a black hole and its immediate surroundings, both the black hole at the center of the Milky Way, and actually the first one was the black hole at the center of the largest nearby galaxy, the one we call M87 in the Virgo cluster. The way you do it is you take a huge amount of video, not knowing how things are going to work out, and then you put it together very artistically. Peter is, as far as I can tell, the leader of Black Hole Initiative, headquartered at Harvard, but involving lots of people elsewhere. And one of the major projects that he's working on is to greatly enlarge the size, the effective size, and therefore the resolution, the ability to see things that are extremely small, of the Event Horizon Telescope, which made the first image of black holes, by putting an antenna on a spacecraft in a fairly high altitude orbit. That, together with the antennas on Earth, gives you a much larger effective antenna, which gives you much better resolution. Anyway, rather than trying to tell you what Peter's going to tell you, I think the best thing is, let's welcome Peter.
It's a great pleasure to be here, and I'm honored to be included in the series of the Nauenberg lectures. I'm grateful to the Nauenberg family. I did know some I had various exchanges with Michael over the years, in the 80s when I was teaching at Stanford, and then in the 90s about some other matters, about Feynman diagrams and things like that. And I always enjoyed his wonderful variety of interests. And perhaps the talk I'm going to give is a lane-changing talk, my sort of peregrinations among these various areas of history, physics, and film. And I'd like to think that Michael would get a kick out of it. He himself was a lane changer at the university best known for lane changing in the world. So it's really a pleasure to be here, and thank you all for coming. Thanks to Eli Silver and Joel Premack and all the others who helped facilitate my visit, so thank you. What I want to do is to look at sort of three topics that are connected in ways that I'll explain, all linked by my interest in the visual, in the material circumstances of science, and connecting the all-too-material with the very abstract. The first is going to be about this book that Joel generously mentioned, Einstein's Clocks, Poincaré's Maps, and the work that extended to with collaboration with the great South African artist William Kentridge. The second will be about the attempt to contain nuclear waste for a period of 10,000 years and what that in various ways meant about time and responsibility to the future, and we'll tell me more about that in a moment. And then the third two onto black holes and where that might go, about thinking about time and making movies of black holes and what that might look like. I began by my work, my PhD dissertation of my first book, were about different kinds of experiments, looking at the way experimenters came to convince themselves that something was real and not an artifact of the experiment or the apparatus, the environment or the apparatus. And I began to see in experiment after experiment this contrast between people that liked pictures, like cloud chambers, bubble chambers, and things like that, and people that wanted to count and do statistics. And both of these, its own culture, not identical with theorists, not just checking what theorists do. I wanted to see what an experimental culture looked like. And that led me to look in a second book called Image and Logic about these two traditions of making pictures, like cloud chambers. You've probably seen pictures of these little particles making tracks inside a cloud chamber, of using film and looking at the particles that skittered along their surface, of bubble chambers that dominated so much of particle physics in the 1960s and into the 70s, and then the unvisual tradition, the tradition of counting and statistics. And each of them was somewhat suspicious of the other. The image people thought that they could really see the processes unfolding, and they thought that the counter people were, they were missing big pieces of the causal structure of things. And the logic people would say things like, anything can happen once. Making pictures of things, that's not good. I want good statistics. And these began eventually to combine in the controllable image in field after field, from MRI images and astrophysical images and across many different domains, combining the logic, electronic, statistical tradition with the image tradition has been one of the markers of the history of the 20th century. And so coming out of that, I became interested in the way that the circumstances under which Einstein and Poincaré worked. It just seemed implausible that Einstein was spending year after year, week after week, day after day, working in a patent office, seeing the most advanced technologies of his time, and that it had no relation to the work he was doing after hours, so to speak, in physics. So I began to look at this and take seriously, what were the patents he was actually looking at? And Poincaré had his own set of metaphors for what he was doing. He said, suppose we want to define what a distant simultaneity was. Well, imagine a telegrapher here who coordinates with a telegrapher there. He sends a signal, bounces back, and uses that to be able to tell how long the one-way trip would be, and then they can correct their clocks. And Einstein said, imagine you were trying to coordinate the time on one train station and another train station. And it became clear to me, as I began to look into this, that these were more than metaphors. They were metaphors grounded in the everyday work that each of them was doing. Poincaré, for example, was actually sending telegraphic signals. He was in charge of the Paris Bureau of Longitude. He was sending signals to people in the Andes and in London and Vietnam, all over the world, and the undersea cables, and using this to set clocks to begin to be able to determine the longitude difference, how much east-west separation there was. So this was a very practical problem. And he was also involved with attempts to standardize the standardization of things. 100 years, after the French Revolution, the French revived their attempt to standardize kilograms and meters, and it was successful. They got everybody, all these countries, to agree. And these was K, the perfect kilogram that became, in one moment, it went from being 1.0001, whatever it was, and they said, now this is the standard. This is exactly 1 kilogram. And these other ones around it were called the witnesses, les témoins, so that anything untoward that happened to K would be witnessed by these other ones. And later on, it became clear that K was actually losing weight, which was a great catastrophe for everybody. But that's the meter stick, M, living in its case on the top here. It was buried, put in an underground vault outside Paris in a great ceremonial event with the plenipotentiaries from different countries, and everyone got to bring home a replica of these to speak standards in their countries. And Poincaré thought, well, I'll use this to standardize time, and we'll decimal, we'll get a decimal system of time I don't like, 60 seconds in a minute, and 60 minutes in an hour, and 24. Let's make it decimal. It was this kind of attempt to revive a French revolutionary ambition to get rid of Sundays, among other things, so that the week would have 10 days. But one of the things they did was to pump time. I love this idea. In Vienna and in Paris, they had compressed air tanks. You can see one here on the left. And the observatory would send down a time, say 12 o'clock, and they'd pump out a pressurized air. It would go to each of the mayoral residences in each of the arrondissements, and it would set the clock to 12. And then people said, well, wait a second, it's taking some time for this pulse to get across Paris. We want you to fix it so it's corrected. So it was a commonplace to start thinking about how long it took to get a signal. This was a slow acoustic signal, essentially, of pressure that went along these pipes. But I love the idea of pumping time under the streets. But time was a vexed issue. It was one that was discussed. It was given great importance. And the British had, at Greenwich, had a time office, and they would determine the time for the empire. This is the time room. And at one point, a terrorist, an anarchist terrorist, loaded himself up with a bomb and came up to blow up the Greenwich Observatory. But bad for him, it blew up on the hill as he was going up. And in the time room, one of them said, "That's dynamite, Mr. Hollis. Spot the time, 4:51." So time over anarchy. But in Einstein, at the Swiss Patent Office, there was enormous interest, a growing interest. Swiss was late to set up their train and their train network, and when they did, they wanted to. It was difficult. It's difficult to lay tracks in mountainous country, but they were very worried about how to coordinate clocks, and there were patents on this. By 1904, the year before Einstein's special relativity, there were even patents on sending signals out. The Eiffel Tower was going to be used, and Poincaré was involved with that in sending out time signals so that boats at sea would actually be able to receive a time signal. So one day, Einstein had been thinking about what becomes special relativity for a long time, since he was 16 at least, and what an electric wave would look like in different frames of reference, and he was really bothered by the generally understood conception of it, thinking about it like a wave in air or water, and that you could catch up to it. He didn't think that made any sense. But one day he was walking. I can say exactly where he was, where that red arrow is, because he said to his friend Michel Bessot, look at the clock in Bern, and look at this clock tower in Muri. There was only one clock tower in Muri, the aristocratic suburb of Bern, and there's only one place you can see both of these from, and that's on that hill. And he said, look at those two clocks. Suppose a train arrives in Bern, how are you going to coordinate the time with Mooring, he said, you would send a signal, a light signal, and bounce it back and take into account the time of travel and then set the clock. So if it took, of course it's much less than this, but imagine it took a second, 2 seconds to go round trip, so it would take 1 second to go. So I'll send the signal at 12, and you'll set your clock in Muri at 12 plus 1 second. So this idea, this simple idea, which fascinated both Einstein and Poincaré, shows up in his paper, he's working on just then, and he said, this was the final piece. Now I know how to complete the special theory of relativity. And it's really what Einstein did to the concept of time that was new. That was the break. The idea that space might change in different frames of reference, that had already been discussed by Lorentz and others, but this was a radical break. And this idea that time and simultaneity could be defined as operations became a model for philosophers and people from many other fields and for physics as a way of what concepts really should be like. So Martial Bourdin, the unsuccessful bomber of Greenwich, then became the model for Joseph Conrad's Secret Agent, which was his most popular book by far, and The Secret Agent became the model for Ted Kaczynski, the Unabomber. There was a sort of a long train back and forth between fiction and nonfiction and reality about time and its place in the world. So I met in around 2009 or so, I think, William Kentridge, the great South African artist, and I had seen his work, which I liked, and he had read this book, Einstein's Clocks, and we started to collaborate on a project that became The Refusal of Time, an installation with many screens. I'll show you some bits of that in a moment. And the idea that I was interested in, he was interested in, was that you would have sort of 3 acts of this, 3 divisions. The river of absolute time, playing on Newton's idea of an equably flowing time. But there were people opposed to that. There were people who didn't like the idea of an absolute imposed time. They wanted a time in their towns or villages set by the sun, the noonday sun. They didn't want to live in time zones. And so this opposition to absolute time, this what became a slogan, "Give us back our sun," became a mantra of people opposing this. Einstein, in his special relativity paper, says there's a peculiar consequence of this account, and that is that a person at the North Pole and at the equator would age differently because one would be in motion and one would be still as the Earth spun on its axis. And then there were people who didn't like the idea that twins could end up of different ages if one was in motion rather to the other. If one went out to a far away and came back, it'd end up younger than the one that stayed home. And the third was this idea of the destruction of information and the debate about what happens if things fall into a black hole. If you throw an encyclopedia in, does it disappear forever, or does it leave some sort of a trace? This is a problem that exercises physicists in a big way. So we began to think about this and to block out the way this might work with a melodrama, with the twins. That's the twin paradox. Exploding Greenwich, that was the representation of this story, the pumping time and Event Horizon. And here's a kind of combination of the various screens. So that in the installation, there were 5 screens and then various megaphones and other things. And this is reducing this 5-screen to 1, which are just a couple of minutes. So let me show you this. So there are many things about this to say, but I'll just make one remark, which is I had, with a filmmaker and colleague and friend of mine, we made several films together, Rob Moss. We had a scene in this film Secrecy that we made where we threw bags of papers off of the roof of a building at Harvard, and they floated down, and we shot them floating in from the sky. And I was telling William Kentridge about this, and he said, well, why don't we play it, we do that, but do it backwards so that the papers rose. And so we did that. His idea was great. And then Data Masilio, this great dancer who's in that scene, and that becomes part of the twin paradox, other things. But when she's spinning around, when it's played backwards, as it is here, the cloth of her clothing, it actually leads her arms. And it's a beautiful effect, totally unanticipated by me. I mean, William maybe saw that was going to happen. But so we played with things, and we had information paradox and things falling, and we used player piano rolls and projected through it. And it was really a wonderful way of a kind of visual, musical, acted out extension associatively to the story of time in the early 20th century. So then that was 2012 that began. There's an associated chamber opera, Fuse the Hour. And I got interested in this sort of weird problem of how do you mark nuclear waste? So the government had this huge amount of weapons waste the Americans and the Soviets made together many tens of thousands of nuclear weapons. And there's a huge amount of waste, plutonium-infested waste in particular, that represented a problem. So Congress said to the Atomic Energy Commission, you can bury this waste, which is what you want to do. Just get the Environmental Protection Agency to certify that you're doing it in a safe way. So the EPA said, okay, well, we know what to do. You take a time of how long something stays toxic, and you protect it for that amount of time. Is it a month or, a year, 10 years, 20 years? Well, the half-life of plutonium is 24,000 years. So you need sort of 10 half-lives, 240,000 years. And the EPA said, okay, well, that's probably more than we can mark things, since that's longer than humans have been on Earth. But you could take 10,000 years, that's twice human recorded history, and figure out a way to mark for the future 10,000 years from now. So the Department of Energy tasked one of the nuclear weapons labs to work on this, and thinking about it provokes us to really think about a lot about what our responsibility to future generations might be, and what communication is, and what will last that we've made, and that really interested me. So one thing, we have a kind of picture that's implicit that goes from wastelands, defiled, to wilderness, the purest of the pure, and it's a kind of spectral extent. That gets complicated in lots of ways by this. And in fact, thinking about the nuclear contamination in the far future causes us to think about time and space in ways that are sometimes quite unexpected. Now, the traditional way by the 1980s of dumping nuclear waste, as it had been during the weapons projects of the Cold War and the Manhattan Project, was to do something like this: fill the waste into 55-gallon drums and dump them and then push up some sand and dirt over them. Not a very effective method. So the Department of Energy said, okay, well, who knows about warning the future? And so they began to look at the people who were thinking about how you predict things 5 years, 10 years, 20 years ahead. And they divided two teams. One team was supposed to think about what the future might be like, in which the waste site would be unintentionally dug into. And then using these scenarios, another team was supposed to design monuments to stop it, so it wouldn't happen. So this is an excerpt from the film, which I think of this as a kind of state science fiction. These scenarios were articulated, and the people you're hearing are the people who wrote these scenarios, and the illustrations are by a great graphic novelist and cartoonist, Peter Cooper.
Here we are in 1990. Call comes in and asks if I would like to participate in a 10,000-year forecast. 10,000-year forecast. I said, you've got to be kidding. And the assignment was produce some stories for us, scenarios, that will depict the next 10,000 years. Stories about what society might be, to help the people who construct the warning markers to understand the different kinds of penetrations that might exist in the future.
What if there was an underground train from Houston to Los Angeles, and the tunneling went right through the WIP site?
We needed what we called a spherical marking system. The markers were not just on the surface, but should be visible however you saw the site. From above, from aircraft or satellites, or from below, whether an underground tunnel or autonomous machines drilling deep beneath the earth.
What's our moral obligation to the future? It's enormous.
What if robots get a virus and they no longer obey their rules? What if people looted the area just the way the pyramids have been ransacked?
We were trying to do scenarios that ended with intrusion, so that intrusion, in fact, could be avoided.
By the way, your colleague, Gregory Benford, was part of this team, and he's a great science fiction writer as well as a very important astrophysicist, and he contributed to thinking up these scenarios, or some of the scenarios. And then the monument marking team said, well, let's look at the past. What do we know from what survived? What do we actually know from the deep past? About the pyramids, about Stonehenge, about the Acropolis. And one of the things that they concluded, the archaeologists on the team, was that what was really successful was the combination of the written and the material, like the Acropolis, whereas things like some of the great Indian mounds or Stonehenge, we can speculate, but we don't really have very definitive understanding of what they are. So they began to think about that, about how to combine writing. They had linguists, and they had people who worked on semiotics, and they had material scientists, what kind of materials. They wanted to make materials that would last but that weren't valuable, and some of the stones at Stonehenge had been carted away, so you didn't want something that would be valuable enough to steal. And so that went on for some time. Then they looked at the Golden Record. They said these were people, Carl Sagan and others were involved in sending out this record that was supposed to be retrievable by alien civilizations sometime in the deep future and figure out something about who we were and what our message might be for what happened to us. So they began to plan for making this underground site. It exists. It's in operation in southeast New Mexico, thousands of feet below the surface in a salt bed. And they began to design these monuments because they couldn't dig until they had a plan on file. And the plan has changed over time, but there was a message kiosk, and one of the ones would say, danger, poisonous radioactive waste buried here, do not dig or drill before AD 12,000. So there were different levels, just don't dig here, then all the way down to a level where it would actually describe what these radioisotopes were and what their dangers were in particular. Some of them, for instance, one of the proposals was to have a spike field that would show that something bad was happening underground here, and you shouldn't go there. And there were many others. There's one, in fact, called Black Hole, where they would cover the part of the desert with dark substances so that it would become very hot and you wouldn't want to be there. Another had all these boulders that made it impossible to settle there. So there are lots of different ideas for this. And then in the midst of making this film, in March of 2011, the triple disaster in Japan struck. And so in a way, what had happened in Japan with the earthquake, the tsunami, and then the meltdown of the nuclear power plants was, in a sense, the nightmare that the WIP site was trying to avoid, that is to say, an escape from containment. And so we went there and filmed in the exclusion zone various people who were living there, who would come back once a month to clean their houses or go various things, trying to keep up a life that might resume sometime in the future. And what was interesting was that we began to hear about the monuments that had been made, some of them as old as 800 years along the spine of Japan, that basically said, a tsunami came up to this point, whatever you do, no matter how many years pass, don't build below this point because you could be hit by a tsunami. And so they began to think about monuments themselves, and one of the things that was interesting was they said maybe monuments were not enough because some of them have been removed or some of them no longer interpreted. People know how to interpret them. One of them got assimilated into a graveyard. But they said maybe a story could work to warn. And this is a story that was part of a paper theater
非常に重要な自分の稲を燃やしてでその稲というのは高台にあるんですけどもそこで全員の村人を火を消すためにというのは実は有名な小説家が書きましてそれが小学校の教科書従いまして当時の小学生は必ずそのお話を学ぶと非常にそれも効果があったと思います。文化的な例えば言い伝えであるとかまたお祭りであるとかこれは人々の活動の中で生きています。生活の中で密着して、語りかけるわけなので石碑などと比べて、その効果というのは高いと思います。
maybe the best way to mark the WIP site is not to have a physical marker, but to have a cultural marker, to keep the memory of the site alive and its true nature known.
Nicky Nuke and WIP Worlds, 11,991. The WIP Museum and WIP Worlds became permanent, off-site, self-perpetuating, and self-financing markers. The deliberately created character Nicky Nuke became the protagonist in stories, poems, films, and other media, carrying the memory of WIP and its dangers into the consciousness of the peoples of the earth. Something as seemingly frail and unsubstantial.
If you had a constant stream of people there for 10,000 years who brought their families and told stories about why it's here, you wouldn't have anybody digging into that radioactive mess.
And in fact, people have built museums at Chernobyl, the upper image there, and people began to imagine what a cultural site might be on the lower left, and there is now a museum at Fukushima that exists. So sometimes the futurists can get things right, maybe not 10,000 years in the future, but the scenarios that they imagined actually have some purchase on our understanding. And what happens in these exclusion zones around Chernobyl and in parts of the Fukushima prefecture is that there's actually a kind of weird conversion of a zone that's contaminated, but also a revival of certain gray fox in the Chernobyl zone or of wild boars in the Fukushima prefecture. You have a kind of wasteland that's protected from human intervention. This is true in the South Carolina nuclear weapons plant at the Savannah River site. You have actually a tremendous amount of biodiversity. The most biodiverse site east of the Mississippi is actually the Savannah River site, which is contaminated. So you have a kind of no longer a spectral, but more of a convergence of these sites into what you might think of as waste wilderness. Okay, so that was finished in 2015, and with a group of colleagues from mathematics, Xingtun Yao, and astrophysics, Ramesh Narayan, Avi Loeb, and with the mathematical physicist Andy Strominger, and Shep Doleman, who was then director of the Event Horizon Telescope, we started this interdisciplinary center. And this is the opening. This is Stephen Hawking in the foreground. And it was a kind of gamble about whether it would work to bring these disciplines together. But black holes, there are many, many interesting things in the sky, but black holes singularly fascinate mathematicians, physicists, astronomers, philosophers. They're just enormously evocative objects. So the idea of what the Event Horizon Telescope, one of the projects there, was that light could be bent around a black hole, and we could actually see the shadow of the black hole. Now, shadows have a long, illustrious history in astronomy. Galileo used shadows on the moon to deduce the height of mountains there, which cracked the idea that the moon was a perfect sphere and violated the tenets of a sort of Aristotelian concept of the sublunary versus the lunar and above. And so you would see these, what we would see would be some kind of bright circle. So that was the idea. And to observe this, we have to build a telescope, a huge telescope, a telescope the size of the Earth, to be able to see something that picks out an angle on the sky like holding an atom at arm's length. So you needed this gigantic telescope. Well, you can't have a telescope as big as the Earth, but you can simulate one by having lots of telescopes and having them coordinate into one array. So this is This was a test. This is the problem is you need all of them to operate at the same time. You need perfect weather practically all over the globe. So this is one of the tests of, this is a radio telescope in Mexico, the large millimeter telescope.
Look at that's the telescope buried underneath that SHIT, if I may say so.
Wait, what happened here?
Weather.
What happened?
Weather happened to us.
This is Shep Dolman on the left.
That's crap.
We can't point and focus through this weather right now. The schedule is supposed to start in 40 minutes. 40 minutes, we know. In 35 now.
When did this happen? Wait, you're shitting me. The last 16 hours, it's been beautiful. And as soon as we come up,
Well, you
like the
arrive at this
gods
time.
hammer us. My biggest concern would be icing,
Yeah,
right?
yeah, we're
Because
pushing it.
if we're
Yeah.
still in the clouds and it gets really cold, it's going to be an ice situation.
Yeah,
That's a possibility.
yeah, that's what I'm worried
Yeah,
about.
I'm really worried about it.
Everybody cross their fingers, use your favorite incantations, and we'll carry through this.
Okay, so we're going to set levels in the other room, and then we'll be ready to go.
I need to adjust the power level of the upstairs a little bit.
Okay, you realize that we're firing this thing off in exactly 14 minutes and
Yeah,
15
I
seconds.
know. Did you say 6573?
So it's RCP and LCP high, right?
Yeah, 1 minute.
There we go, people. Hold on to your hats.
Okay, we're ready.
4, 3, 2, 1, 0.
So this has to be repeated all over the globe. We have each of these telescope arrays has to be working and synchronized in good weather, because you have these photons spending 55 million years coming to the Earth and then get stuck on a raindrop. It's no good, right? So then you might ask, well, what kind of images is this? It's not visible light, but are we seeing when we say we see a coyote or a fox or something in the infrared? We think we're seeing it, right? We recognize that. Are we seeing when we see a silhouette? Roger Deakins is one of my favorite cinematographers, but we still think we're seeing a woman walking down the aisle, or we're seeing soldiers on the horizon, or we're somebody running. I mean, we still think we're seeing when we're seeing a silhouette. So or when you say to make an image out of this, we get petabytes of data. We have to coordinate all these telescopes to get them lined up, and then at the end of the day, we have to take that information and use it to make an actual image. Well, what kind of thing do you have to assume to make an image? Well, suppose I ask you, separate the blue dots from the red dots. Well, you would say, well, what do you mean, separate the blue dots from the red dots? Do you mean like trace out so that no blue dots are left of the line and all of the blue dots are on one side? Or do you mean find the sort of best curve or best ellipse? You have to tell me something for it to be well defined enough to answer the question. And essentially your cell phone does that. I mean, it's a computer that's using its computational skills to make the different kind of images. When you say you want a portrait style, or you want black and white, or you want to have different white balance. It is a tremendous amount of computation. But we say we're taking a picture when we take a picture with our cell phone. They are I mean, hardly anybody would use an analog film anymore. So photography is a much more extensive thing. You can have photography without cameras. You can have photography without film. Digital or computed. And so what counts as a photograph has shifted over time. Now I want to pause and say something else about this struggle to get an image that we could trust. So this is 200 people across 20 countries, all trying to make this work. Instrument design, instrument makers, electronics experts, computer vision people, modelers, theorists. It's this massive effort by astronomical standards, not by high-energy physics standards, but having 200 and then 300, and now there are 400 people in the collaboration was pretty big by astronomical standards. So in separate work from the black hole, Lorraine Daston, a historian of science and a long-term colleague and friend, and I wrote a book called Objectivity. And we were interested in what that meant, that objectivity is not the same thing as science. Objectivity was something that gets created in its full form in the 19th century. There's plenty of science before the 19th century, plenty of physics before the 19th century, but objectivity, as in a sense that I'll describe in a moment, was something that was born in the 19th century. In the 18th century, and I'm being very schematic, the kind of images people wanted were perfected. They were idealized. That's what you wanted. That's what Goethe said he was trying to do when he made an Ohrpflanz or something. Or when Albinus drew the skeleton, he didn't really think that there were skeletons dancing in front of white rhinoceroses. This was an idealized form, and he corrected things in the skeleton to convey that perfection. So in this cartoon version of what we argued in the book Objectivity, you had a sage or genius. It was a scientific self that was that. Images were metaphysical. They referred to the perfect form behind any particular skeleton. The practice was one of intervention and fixing up. And the ontology, that is to say what the status of these skeletons or leaves or insects were, was of a universal. It was the plant behind plants. It was the insect behind insects. It was the cloud behind clouds. And that then, in the 19th century, people began to say, that's not what we want. What we want is to see things as they are in their particularity. This example, for instance, by Otto Funke, played an important role in understanding the role of oxygen in the blood, and he said, I'm going to draw what I see in the microscope of these crystals, even the deceptions. Now, the idea that Albinus would draw even an optical deception would have been anathema. He would never do that. So this is a pretty big change. And the idea was to be as mechanical as possible, to transfer nature to the page. And Rudolf Virchow wrote, I must openly confess it has not been possible for me to desubjectivize myself entirely. With each year I recognize again that in those places where I thought myself wholly objective, I've still held on to a large element of my subjective views, my opinions, my representations, my theory, my speculation. And so from the 1830s forward, continuing to the present, as the idealizations also continue to the present, you have more of a worker, like making sure that all the forks or bullets or whatever it was are identical. Nobody wanted people to improvise and making each fork a little different in the age of mechanical production. And so the practice was one of mechanical transfer, and the ontology was one of individuals. Then, in the 1920s and 30s, people began to realize that this adherence, this rigid adherence to just drawing what you see or representing what you see could lead to real problems. Scientists had gained enough confidence in many areas to be able to say, I know when my instrument is misbehaving and when it's producing an artifact, and I'm going to fix it. And they would say things like, a certain subjectivity to these charts is necessary. This is mapping solar magnetic fields. And you see that pretty often in the 30s and 40s and 50s. So the expert needed to use judgment, trained judgment, not I'm a genius so I know what it should look like, but I've trained. I've trained to recognize the difference between a grand mal seizure and and other forms of seizures. So you have this sequence of truth to nature. This begins in the 18th century, this idealization becomes mechanical. You have an introduction of mechanical objectivity in the 1830s. You have trained judgment that becomes sort of a self-confident scientific view about how to remove artifacts, for instance. And then the computed images become more and more a part of the work across many branches of the sciences. So back to the Event Horizon Telescope. These are these petabytes of data. They come in big hard drives, have to be specially made, carried down from mountains, packed up in Federal Express and sent to the supercomputer where they're all put together. And essentially, you're using the Earth itself as an instrument. As it spins on its axis, it fills in the virtual picture of the world, and you begin to arrive at an image like the one you've no doubt seen. So then the question was, how do we know we're making the right image? How do we know, as we reconstruct this image from this data, that it's reliable, that it has a certain form of objectivity? Well, we took synthetic images, imagined pictures of black holes, imagined pictures of things randomly chosen off the internet, and sent them out to 4 different groups that were not allowed to talk to each other. And each of the groups then got the data and said, make your best image. Just whatever you do. You can do anything you want. Make the best image out of this data that we've sent. And the original data, the ground truth, was Frosty the Snowman in this instance, because nobody could possibly guess that that's what we would send out, right? So each of these are different methods here, and you can begin to see that they're getting more or less, sometimes more accurate representations of Frosty. And once everybody could reliably, so this is the secret, this is at the Black Hole Initiative, so putting up light, transparent blocking sheets so that other groups wouldn't see what it was doing. And then then we said, okay, now, on the 5th of June, 2018, distributed real data. So each of these 4 groups, various places in the world, got the data at the same time, and we said, do your best, use the techniques that you've used to reproduce known data, now do it. So this is the moment, the first time that we saw, this is in one of the groups.
For me, I'm not, I'm just saying, I think it'd be fun for us all to do the first one together, see that it's shit, and then go off in our own little ways and fix it. I mean, I think it's just it's so exciting that do you want to do it alone?
I would like to see it all together so we can get some idea of the data.
Are you ready?
Ready?
I'm ready.
Ready? Is that going to work at all?
I'm going to do enhance.
Ready?
Set.
Go. Oh my god! Oh my god, we pressed go!
It's just a waffle. Ah, that looks really, really interesting. How's the waffling going?
Andrew's looks beautiful, but there's no tweaking involved.
Because I have compactness very high.
With a huge.
I think Daniel and I were both getting something like this.
Okay.
That's what I get when I use only closure.
Only closure.
Oh my god, look at the chi-squares.
That's pretty good.
And coverage. And then this is, after a few more iterations, it smooths it out and gets rid of some of the extended jump.
This is on mobile? Or?
Is this only one day?
This is only one day.
You know what?
That's pretty suggestive.
Well, it seems...
Did you remove these outliers in the amplitude?
I didn't touch anything.
That is very cool, guys. That's really, really cool. Which one is that?
This is Katie's image.
See, it looks different though. Because you guys have a bright spot more on this side.
Okay, seriously. but we're all getting kind of a crescent that's
all
about the right size.
So what is the size on that? It's like 40?
This is about 40.
Yeah.
Okay, we'll get that. That's what you expect if
See, look.
M87 has 6 billion solar masses.
Yeah, it's a high mass case.
You know what this is? This is a scale to weigh black holes.
So this is expert judgment, and we then got the teams together to see if they looked alike, and they did pretty much. And on the 24th of July, we had a consensus that these images were very similar. You could compare them pixel by pixel. But then the real question began, were we all fooling ourselves in some way and finding something that wasn't there? So we'd been tuning, the various things to tune, knobs, so to speak, how smooth the image was, and the equivalent of asking sort of what kind of separation do you want between the blue dots and the red dots. And so we said, okay, now let's let the computer try out all different settings, like telling you had an automatic camera and you said, try out all the f-stops and all the shutter speeds and different lenses and see what you get. So we took a training set, crescent, ring, disk, 2 blobs, and said, computer, figure out the settings that gave you the best reproduction of that image. This is fake data that we put in, and said, computer, teach yourself find yourself the best settings, and then take those same settings and use it on the real black hole data. And what the computer got was something very much like what we were seeing. So this is now more like mechanical objectivity. So we went from expert judgment to mechanical objectivity, and then the question was, should we average the different images? And people had big argument, nothing really corresponds in the data to an average, or should we, is it good to average so we don't confuse the newspapers, or should we average so that we don't privilege one group's image over another group's image? And in the end, we decided to average because it was the most conservative way of proceeding. It was an image that captured the things that were in common from the different images and suppressed the things that were idiosyncratic to one image rather than another. But that was a decision. And that's a form of idealization. So in a sense, we played history backwards, that history went from idealization to the mechanical so history went from idealization to mechanical to trained expertise. We started by saying, use your expertise, then we went to the mechanical, and then we idealized by averaging. And then on the 10th of April, 2019 at 9:07 a.m., it was announced all over the world, all the different participating countries made announcements of this image. It had to be timed so that no one group would have priority over the other groups. And I was down at MoMA and talking to some of the people there with whom I've collaborated before, and they said, well, we have to have this for the permanent collection, photography collection. So there's now a picture of M87 in the Museum of Modern Art's permanent photography collection. But almost immediately, we wanted to know, is there more physics that could be extracted from this? And so we began to wonder, a group of us, about whether there could be light that was actually set into orbit around the black hole, not just the hot gas.
There's something about us as human beings that we really want to know what's out there in the universe. And I think like 1 billion people saw the first image of the black holes. And I think we just want to know more.
But most of what we saw in that picture was gas circulating around the black hole. We would like to understand the properties of the black hole itself. It turns out that there is a really elegant, beautiful, and simple way of doing that.
The black hole space-time itself actually creates a way of studying black holes in an entirely new way.
Black holes are where you have the strongest gravity. Light rays are bent round. Are bent round by a lot. Can even make a circle around the black hole. And this leaves certain signatures in the image of the black hole. The photon ring.
Those photons tell you everything about the nature of the black hole.
We'll be able to probe principles of general relativity, gravity, and how the universe works on scales not before seen.
So the idea would be to have a satellite linked up to this network on the Earth, so it effectively would make a telescope not the size of the Earth, but of 5 times the size of the Earth. And so this would be, this would then link to the various stations on the Earth, and we would use it to try to capture these rings. So in a sense, what these rings are, it's an infinite series of rings corresponding to photons that go around once and come to us, go around twice and come to us, 3 times and come to us. So in a sense, stored there is a kind of picture, in principle, don't try this at home, of the whole visible universe, captured at different times, because the 2 rings get stored there for, say it takes a week to go around, once around, stored there for a week, twice around, stored there for 2 weeks, 3 times it's stored around for 3 weeks, but we get them at the same time. So if you could magically, with the cosmic eye of a lynx, see these rings one after the other, it would be seeing like frames of a movie of the history of the visible universe. And so the idea is that we're
whole
putting together
project
now
is
is to
light
try to
all the way
make
down,
such a
from
satellite
the
led
black
by
hole
Michael
to the
Johnson.
satellite. Looking at just pure light, the way it moves, conveys the geometry of space and time itself.
Powerful jet emitting so much. We do not have a complete theory of how to describe a black hole. This experiment is an exciting step in that direction.
So we finally have technology good enough. Now's the time. Strike while the iron is hot.
This is actually the inception point, and I get to be on the ground floor.
We're looking at something like a 3.5 meter aperture.
Trying to lead it, trying to be responsible for the vision and make sure that we're going after something that really can be done. It's thrilling to have that opportunity.
The photon rings illuminate the geometry of our universe. That seems to me something worth fighting for. It's a 10, 12-year project, requires a certain amount of optimism and hope, and something I really believe in.
That's how knowledge evolves in bits and pieces with the contribution of hundreds of thousands of people, and I'm just happy to be a part of it.
8, 7, 6, 5.
Yep, this is why I get up in the morning, and I can see it. I can see it clearly what we're going to see, and every day I think, yep, we're getting one step closer
3,
to that.
2, 1.
So what would we see, or what could we hope to see? Here's a simulation of what, on the right, you see of the photon ring and the swirling gas. And what's interesting is the photon ring is stationary. It's just fixed there. Everything else is in motion. So if we could see a movie of this, which is one of the things we're aiming for, we could distinguish between the artifacts of tendrils of the accretion flow and so on, and this structure of light, pure light, around the black hole. And that would be amazing. That's our goal. So here's an example of a movie now inside of the science itself, one that would tell us about the structure, the geometry of space-time near the horizon, near an edge of the universe. Thank you.
Thank you, Peter. That was amazing. And there's time for questions. So don't just ask a question. There are people with microphones, and raise your hand, and they will come up, and please speak in the microphone. And it's not just for us, but the people on Zoom will not be able to hear what you're saying unless you have the microphone.
There's something that one should make clear about these pictures here and the real observations, and that is that this is radio emission here that we're seeing here. So that's rather different from the gas which is swirling and going into the black hole.
Yeah, you're saying that this is radio emissions from, well, what we're seeing are two different things here. There's the hot gas, which emits in the millimeter wavelength. We choose that wavelength because it's good at penetrating the dust and junk in space, and also gets through the atmosphere in a reasonable way. And then there's light that's in orbit, some fraction of which escapes the photon ring. There's a critical curve around the black hole, and anything that goes towards the black hole from that critical curve falls in, and anything that's even a little bit outside of that escapes to infinity, or could escape to us. So some fraction of the photons of each of these rings will escape to us, and that's what we're trying to see.
So you said photon ring. Does it just happen to be facing us, or is it a photon sphere?
It's a photon sphere, but no matter where you were, you still would see it as a ring. But it would look slightly different depending on the inclination. So M87, the supermassive black hole, 6.5 billion solar masses, that's at the center of the Virgo, of the M87 galaxy, which is a huge galaxy, produces these jets that go out the distance of galaxies. And those jets, which were seen as early as 1909 by an astronomer named Curtis, is an indication that this thing is spinning pretty well. And that when a black hole spins, it spins up the magnetic fields into helices that sort of come out of its poles, so to speak, and that sucks up some of this plasma, this hot gas that's around it, and that shoots it out. That's the standard account of what causes these jets to form. So one of the things we really want to do is to be able to use this photon ring by its shape, we could tell how much the black hole was spinning. There are only two real things you can say about a black hole: how massive it is, that is to say how big it is, or how much it's spinning. But it's very difficult, and it's been a long struggle to try to determine what the spin of black holes are. And if we could know that about a number of black holes, we could say something about their origin, about these supermassive black holes. Were they produced by a series of mergers getting bigger and bigger? Two little black holes make a medium black hole, and medium black holes combine and make a big black hole. But that's the idea. We would like to be able to develop a method for on the astronomy side. The photon ring would tell us something about the origin of these jets, about how much spin there is. On the physics side, it tells us something fundamental about the nature of space-time near the horizon. So it's an experiment that, if we can make it work, would have two arms, one gesturing towards astrophysics and the other gesturing towards the nature of space and time.
Hi, great talk. What other black holes are you planning to image? Like the center of the galaxy, for instance? Or?
So there are two black holes that are big and bright enough for us to be able to have made those original images with the Event Horizon Telescope. One was M87, which is 55 million light years away and 6.5 billion solar masses, and the other is about 1,500 times closer at the center of our galaxy, Sagittarius A star, and it's about 1,500 times smaller. So it's like the moon and the sun. They're approximately, as we know from the eclipse, they're about the same size on the sky, but one is much bigger and farther away. So the idea would be to look for the photon ring on those two cases, where we have a lot of detailed information, and then to study things like how the polarization pattern of the stuff around the black hole, and then use that to be able to look at a lot more distant black holes or fainter black holes, and to be able to say something about their spin. So it's sort of two steps. First, really understand the photon ring and from the most accessible black holes, Sagittarius A star and M87, and then use that as a calibration to extend to, say, 10 more sources. So that's the goal.
Could you relate the first part of the talk to the last? How did you handle synchronicity when you're comparing pixel by pixel with all of those different places? And what error does that potentially introduce?
So the first thing we wanted to know, we had these 4 different methods for imaging the black hole of M87. And we wanted to know whether how much alike these images are. I mean, were they likely to be the same image? And so you can do a pixel by pixel comparison of sort of make a chart of, method 1, 2, 3, 4, method 1, 2, 3, 4, and ask for the correlation in each case and sort of fill out this grid. And they were all upper 90%, similar, method 3 with method 1, method 4 with method 2, and so on. And it's that quantitative assessment that led us to think that these images being produced by these 4 different methods were producing something that was highly correlated, that was the same in some statistically specifiable sense. So there was not a time development here, but it's a relevant question. The M87 takes takes days to get around. So we had to essentially take a picture all night, and that's okay because a 12-hour night is a small part of days, many days. And so, it's like taking a picture at 100th of a second of a car that's going in front of you at 30 miles an hour. That's all right. It's not changing that much in the 100th of a second. The problem is that for Sagittarius A star, the black hole that's at the center of our galaxy, it changes on a scale of minutes because it's 1,500 times smaller. So, a minute in the life of Sagittarius A star is like a day in the life of M87. So there, it's like taking a picture over 10 seconds of a car going by you. What you'd end up seeing is just at night would be just a bunch of red light, red streaks and white streaks. So that's figuring out how to handle those sorts of problems. And the fact that since the Sagittarius A star is the center of our galaxy, which is like a plate, and we're out maybe a third of the way from the center, and the black hole is at the center, it's going through all the dust and junk in our galaxy. So it's messier in these various ways. So the Event Horizon Telescope, the we in that sentence, it didn't produce that image until May of 2022. So, there was the pandemic, there were lots of other things going on in the world, but from April of 2019 to May of 2022, it was 3 more years to make an image of Sagittarius A star. And so, because of this problem that things are changing all the time with Sagittarius A star, we'd like to be able to make movies of it. Put aside the photon ring for a second, just of the hot gas, the billion-degree gas that's going around, the plasma that's going around the black hole. We'd like to figure out what's going there. Sometimes there are flares on Sagittarius A star, and we'd like to understand what happens to those flares. Does it create a bright spot which you could track going around? Could we understand some of the dynamics of what's going on there? So that requires making movies of that. That's one of the things that's under intense work right now. And it's difficult because things change quickly with Sagittarius A star. So the connection to, many connections between special relativity leads to general relativity. General relativity is the foundation for basically 100% of what the second part of black holes and everything that's in the second part of the talk. But in addition, what interested me is that making these movies, which we're trying to do, is essentially the movie becomes not a movie about the finding of the image, but movies that are there because we are looking at a time-varying structure in the sky, and we want to be able to see how that changes to understand its dynamics. And the same is true, even more so with the photon ring, that being able to see, if we could see something static, the photon ring, and other things moving, that would really convince us that we were seeing something that it was the photon ring we were looking at, because the photon ring doesn't change, and the swirling plasma does. So movies become, understanding how time plays out in these cases tells us about the reality of the phenomenon we're looking at. It's part of the evidence basis.
I think there's a question from Zoom.
Yeah, so it says, alt history question. So if the other side had won at Trafalgar, or if Waterloo had never happened, would the prime meridian pass through Paris?
So this is a good question, and it refers to the fact that in the 19th century, there was a battle over these time zones. And it was essentially driven by the trains. That, if you took the first time zones were train tracks. They're 3 feet wide and hundreds of miles long. If you took a train from Los Angeles somewhere, and the train originated in Los Angeles, it was Los Angeles time that determined the time all along the train track. And that was okay if you just had trains going certain places from Los Angeles or from Chicago or New York, but at a certain point they began to cross. So what happens if you have a train track that starts in New York and it gets to some town, and another train that's the train track that comes from Chicago and it crosses there? Then you have 3 times. You have the New York time of one train track, the Chicago time of another train track, and the local time of the town where you are. So the train companies voted. You got 1 vote for each mile of track you had. And so Leland Stanford got a lot of votes. And they voted and they decided to partition the country for train purposes into these sort of orange peel slices. They're the zones that Pacific time and Mountain time and Central time and Eastern time and so on. And they were set, the idea was that they would set it on the basis of a 0 of time at Greenwich. Now, next to London, part of London. And the French didn't like this at all. And they thought that a great place to have the 0 of time was in Paris, at the observatory next to the Garden of Luxembourg. So there was this pitched battle between the French and the British, as there often is. And the French suspected that the British were kind of paying off the smaller countries, a kind of coalition of the willing, of en la lettre, to vote in favor of the British. The British said, well, 90% of the world's shipping uses, Admiralty maps. And the French said, commerce, you're deciding this on the basis of commerce. It should be based on scientific principles. And then the French tried to make it in, an island, of historic interest, and then the British discovered that the island wasn't where the French said it was. It was really just a 20-degree offset from Paris. And then the French said, well, how about the Bering Strait? We could use that, could slicing the work. Well, anyway, the British won, and it became the 0 of longitude, and then every 15 degrees, 1 for each hour in time zones. And then, of course, there's politics, and some of the lines go like that to put countries in the same time zone, or so on. But the suggestion in the question was that if history had played out differently, and the French had been more powerful and the British Empire less successful, could it have been centered, the 0 of longitude, at Paris? And the answer, I would say, would be yes.
Hi, thanks for the great talk. So you'd mentioned in one of the questions here how measuring the polarization of these rings. What's the interplay between the spin of the black hole and that polarization, and then in these interferometry experiments, how do you actually measure that?
So, great question. So there are two different things. One is each successive ring is oppositely polarized to the one before it. So you have one ring, the photons go around once, and another one go around twice, and 3 times. And it's like if you had one of those child's windmills. If you go around the back, it looks like it's spinning. If I look at it, it goes around this way, and you see it going around the other way. And essentially, we classify the rings by the number of actually half orbits that they make. So what you're seeing is if you go around one more half ring, you get a flip of the orientation. And that's so the polarization flips from one. So that would be a good test for really seeing the photon ring. If you saw, say the n equals 0 case, basically the hot gas case, and compared it to ones that went half a round more, you should see a flip in polarization, and the next one another flip. That's one way that polarization plays a role in simply determining whether you're really seeing the photon ring. Okay, that's part A of the answer. The second is that even if you're looking at a black hole, even if you can't resolve it, you can't see the dark depression at the center, you can't see the shadow of the black hole, you still could look at the polarization around it. And that polarization, where the electric fields go, is related to the spin of the black hole. So what we'd like to do is to learn about this in detail from the two big targets that we can measure in detail, and then to use that to look at black holes where we can't see the center of depression, we can't see the dark shadow, but we can see the polarization. If we could do that, then we could get the amount of spin, at least approximately, for a larger set of black holes. So, astronomers have I don't come from astronomy, I came out of physics on the science side of my work. And so one of the things that I've learned is that astronomers are conflicted in one way. On the one hand, they'd like to have a good particular target, like the sun. There's a whole branch of heliophysics. Nobody complains there's only one sun. Or maybe they do, but they're used to it. And but there's another side of astronomy that says we don't want one target or two targets. We want lots. We want lots of neutron stars and lots of binaries and lots of and so one of the things that we'd like to be able to do, if we could make this bigger telescope, this one that included space, would be it gives you much more resolving power, and you could start to see these other black holes. In a sense, you could say, well, got two visible black holes. That's twice as good as heliophysics, but that's not what astronomy also wants. So this would give us a chance and then to see things like there's one candidate that might be the merger of two supermassive black holes, and we could actually see that with much better resolution. So there are other things you could do, but the thing, at least for me, other people have different things that get them out of bed in the morning. I get out of bed in the morning thinking, I want to see the photon ring. And then, if we could do that, we could do other things like look at what they call demographics, a lot more black holes, even though 10 is not a very big number, it's bigger than 2, and other things as well, like maybe say something more about the mechanism by which these jets get shot out. There's a standard account, the one that I related earlier, that says that black hole spins, it spins space around with it, and when it does that, the magnetic fields get spun around and they end up in these helical structures that then suck the plasma out and shoots it into space. So maybe we could say more about that, and is that mechanism right, or more right than sort of the standard alternative?
Thank you. I think at this time we should end the formal part. Thank Peter. And outside there is a reception with some refreshments, and you're all welcome to join us. So thank you very much.
Thank you.